Cool. Well, thank you all for being here. It's an honor and a pleasure for us to be here. This is my colleague Arpan. He will. So the way this will work is I will give an introduction to neural networks, and then he will show this wonderful tool called Tensorboard that helps visualizing them. So just as a start, I'd like to see how many people here are familiarized or work with neural networks in their daily life. Cool, quite an educated crowd. I want to hear what's your favorite application of them? Anybody?
LSTMs.
LSTMs, yeah, recurrent neural networks, sequence generation. Any others? So I have a bunch of favorites, mostly like game playing. I like when a computer can beat a human in Go, or also in Jeopardy quite badly with IBM Watson. Or the coolest one is self-driving car. Or other pretty cool ones like spam detection, image recognition, finance, medicine. Many cool applications, and they all involve neural networks. But I like to go back to the basics and actually think of this question: what is a neural network? And so if you know them, or if you don't, think of the moment when you first heard the word neural network, and what was that mental image that you had. If it's anything similar to mine, mine was something along these lines. I just picture like a robot with a brain and some liquid and claws and something pretty scary. But then I started working with neural networks more and understanding them more, and I realized that they're actually a lot scarier than that. When I saw this, I wanted to faint. Complicated structure with nodes and edges and information passing in and coming out. But then I worked with them a lot, and I tried really hard to really grasp the concept. And when I think of a neural network, I don't think of this. I think of this. Think of a kid playing in the sand, and there are some fake-looking Photoshop red shells and blue shells in the sand. And I asked the kid, "Hey, can you draw a line and separate the red shells from the blue shells?" And the kid does that. So that's pretty much it. Your goal is to classify data. So we have some points that are blue, and that's, say, positive, and some points that are red, say, negative. And we want to draw a line that cuts them, or maybe a complicated surface that cuts them. But the idea is to split data into two. So let me go through a quick example just to wake everybody up. Let's say we are an admissions office at a university, and we're accepting students or not, and we have two pieces of data, a test and grades. Okay, so we have student number 1 who got a test 9 and grades 8 out of 10, so that student got accepted. Then we have student number 2 who got 3 in the test and 4 in the grades, that student got rejected. And then we have an incognito student number 3 who got 7 and 6, and the question is, do we accept them or not? So we want to make a model to predict this, right? So the first thing to do our model is to plot them in the plane. So the student who got 9 and 8 gets plotted in the 0.98, and the one who got 3 and 4 gets plotted in the 0.34. And now we do what we do in machine learning, which is we look at previous data. So this is our previous data. It's all our points, students from before. So as you can see, if students did well, they get into they're blue, so they get accepted, and if they didn't do so well, they're red, so they get rejected. And now a very simple quiz for you guys. Does the student get accepted or not? I see some yeses, some no's. Who says? How many say yes? Cool. Anybody say no? So the student does get accepted because it looks like this line is sort of our model. This line is breaking the data in two. And the student goes somewhere over here, so that person gets accepted according to our model. Okay? What if we have more columns? That's no problem. If we have something like class rank, well, we can just, instead of plotting it in 2D, we plot it in 3D. Then our data looks like a bunch of points flying in 3D. And our model is not a line anymore, but it's a plane. So in general, if we have n dimensions, our model is just going to be an n-1 dimensional hyperplane cutting the data in two. But now there's a question. And the question is how to find this line. So I'm going to show you several ways that they're actually all pretty much the same way. So let's say our goal is to split this data. We have these 3 blue points here and these 3 red points, and we want to cut them. So how does the computer start? Well, by drawing a random line and trying to get a little better and a little better all the time. And so randomly, we're going to say, we're going to move this line to try to improve what we're doing. So we're going to ask every point, what does it want? Right? Every point wants to get eventually well classified. So here we have the blue points in the blue area are well classified and the red points in their area. And the 2 points on the left and the right are misclassified because there's a red in the blue area and a blue in the red area. So if we ask the points that are correctly classified, they all say, I'm good. What will the other 2 points say? What will they tell us? So here's another easy quiz. We have a red point in the blue area, and it's misclassified. So quiz, does the misclassified point want the line to move closer to it or farther? Who says closer? Who says farther? So actually, in order for the point to be classified in the correct area, it wants the line to move closer. Because if it moves closer, then it has a hope of one day being in the correct area. Okay? So now basically, we ask every point. The correctly classified points say, I'm good, don't worry about anything. And the other two say, come closer. So we move the line closer to them. Closer to one of them until it passes. And then closest to another one until it passes. And that's it. So that's called the perceptron algorithm. Okay? And there's a way to get the line to move closer to the point by actually taking the point coordinates and adding them to the parameters of the line in a certain way. But let's do this a little more formally. The way we do this more formally is by introducing an error function. So an error function is basically telling the computer how badly it's doing to solve a problem. Like if my problem is, for example, finding that glass of water, a human can easily just go to it, but a computer kind of you have to give it some metric of how badly it's doing. So the metric would be the distance, right? Like how far am I from the glass of water? And then I move around to see how I get closer. And as I minimize the distance to the glass of water, then I solve my problem. Here's another example of an error function. Let's say we're standing at the top of a mountain. It's called Mount Everest. And we want to descend the mountain. So what would the error function be there? How do we tell the person how far they are? Because, well, if we think about it, we can just descend the mountain, right? It's easy, right? But let's just say it's cloudy. And we can't really see around us. So if we can't see around us, all we can do is we can look around us and say, okay, in what direction can I take one step to get closer to the floor or to the bottom of the mountain, right? So what we want to do is we want to minimize the height, right? If we can take one step that minimizes the height the most, then take that step. Let's say it's in this direction. So we take that step, and then we do it again. We look at what direction will minimize the height the most, and then take the step in that direction until we're in the bottom of the mountain. So basically, if you want to descend from the mountain, you want to minimize the height. Now our problem is splitting the data. So what do? We want to minimize something. So we have to come up with some error that when we minimize it, we have solved our problem of splitting data. So let's go back. And what seems like an error function we can use? Like what seems like something we can tell the computer how badly it's doing?
Squares distance.
Square distances works, yeah. Let's go for something much simpler. Let's go for like the number of errors. Okay, so like you have 2 errors. And so we're going to say, okay, move the line around to see if you can remove any of the errors. So let's say we move here and we're doing a little better. Let's say now we have 1 error. Now we move here and we have 0 errors and we're done. Is there any, does that look legit or does that look like I slightly cheated? Well, there's some slight problem here. The problem is computer can only take, like we only want to take small steps because we don't want anything to go very chaotic. If we take tiny steps and I tell the computer, okay, you got 2 errors. Now take a tiny step. 2 errors still. Take a tiny step. Still 2 errors. Take a tiny step. Still 2 errors. When I mean tiny step, I mean derivatives, right? So like you really can't do that. And this is kind of like instead of descending from Mount Everest on the right, we're trying to descend from an Aztec pyramid, which has just stairs of like 2, height 1, height 0, like 2 errors, 1 error. And we try to descend, and anywhere we take a tiny step, we see that the height is 2, and there's no way to actually find the place where the distance is 1, so we get confused. Whereas in Mount Everest, we can detect very tiny variations of height, and so we can actually descend properly. So what that means is that our error function cannot be something discrete or something with steps. It has to be something continuous. As a matter of fact, it should be differentiable, so we can take the derivative and descend. So what we're going to do is come up with the log loss function. And so the way I see the log loss function is basically we want to punish every point. My animation is not working, sorry. Oh no, it is working here, sorry. 1 second, technical difficulties. So we want to punish every point. And so the points that are misclassified, we punish them a lot. That's why you see the big size. And then the points that are correctly classified, we don't punish them much. So we see them as tiny. And actually, as you said, the error is based on the distance from the line. It could be the square. It could be actually, it ends up being the logarithm of something, which at the end ends up being a linear function of the slight linear function on the distance of the line, and almost 0 for the points that are correctly classified. And then at the end, we just add all these errors, and then we get the error function. Okay? So now I have something continuous. Now I have something that I can actually take steps to decrease. So I just do that. I take steps to decrease this function as much as I can until I get to a point where this is minimal. I have a much smaller error, and then I've solved my problem. So we minimize the error, and we used gradient descent. Okay? This slide is here just to show off my animation skills. There's the error. As you can see, is the sum of blue and red. Then we take one step, which takes us here, reducing the error a bit. Then we take one step again, calculate the error. Take one step, which brings us down here. Until we minimize the error function. So we've answered our question. In order to, the equivalent of minimizing height to descend from the mountain is minimizing the error function in order to split the data. But now the question is that was kind of like a little vague when I said you take a bunch of steps in all directions and see where you descend the most. Computer's not going to try that. What we really want to do is use calculus, right? So here in Mount Everest again, the error, as we said, is the height. And in order to find this direction to go, we actually take the derivative or the gradient if we are in many dimensions. But basically the gradient tells us a function where does it increase the most. So the negative of that tells us where does it decrease the most. So all we have to do is take a step in that direction. And so what is derivative? Derivative is rate of change. So let me show you how I think of the derivative of the error function. Let's say we have a point, or the rate of change of the error function. Let's say we have a point here. It's misclassified because it's red in the blue area. So it's got a big error. And now the question is, how do we make the error change? Because it's rate of change of the error function, right? So quiz. Where should the line move to reduce the error? Closer or farther? Closer, right? If I move it closer, I am decreasing this error. Now, quiz number 2. If I have a point that is correctly classified, where should the line move to reduce the error? Farther, right? Because the point that is correctly classified has a tiny error, but it's even tinier as it gets well into its correct area. So this is farther. So when we take the gradient of the error function and take a step to minimize it, we are actually just asking every point, what do you want? So the correctly classified points say go away, and the incorrectly classified points say come closer. And then the line just listens to them every step by step, until it finds the perfect solution. So it looks very similar to the perceptron algorithm, right? It's actually the exact same thing. If you calculate the formula, it ends up being the exact same thing, except this is continuous and the other one is discrete, but we can talk a little bit about that. So far, any questions? Far so good? So there's one thing that I kind of swept under the rug, and it's what is the error function, right? It's a function, a formula with some logarithm or something. So let me actually tell you what the error function is, okay? So in order to, we've seen that, in order to explain the error function, we have to see what's the difference between a discrete and a continuous prediction. So the predictions that we've been doing so far are discrete in the form of yes, no, right? The student got accepted or did not get accepted. Turns out that this is not going to help us out with derivatives because it's a step function. So we actually want a continuous prediction. A continuous prediction is of the form a number between 0 and 1. So if I say, instead of saying the student got accepted or not, I'm going to say the student is 63.8% likely of getting accepted. That's going to be how our answers are going to look. And so instead of zeros and ones, or yeses and nos, we're going to actually give numbers between 0 and 1, which give probabilities. So the points that are well in the blue area have things like high probabilities of being blue, the points of, and they are being accepted. And then the red area, they have like low probabilities of being blue, or the student getting accepted. So really what we want is not just a line that cuts data. We want an entire probability function, right? We want our main line to be the 50-50 line, where you have the same probability of being blue and red. Our red area being where you're more likely to be red, and our blue area where you're more likely to be blue. Okay? So something like this, for example, this point has 50-50 chance of being blue or red. This point has 40 of being red and 60 of being, sorry, this one has 30 of being blue and 70 of being red, and this one is like 80 of being blue and 20 of being red. So it looks like this. And how do we build such a probability function? Well, the way we do it is combining a linear function and something called a sigmoid. So this is the, we're going to do it linearly, right? Instead of having just a line, we draw a line, and then we find a separation, and we draw a line labeled 1, 2, 3, then labeled them -1, -2, -3, etc. And now we have sort of a measure on the blueness of every point. And then we want to take a function that takes all the numbers and crunches them into the interval 0, 1. And that's what we do over here. So the function we're going to use is an activation function. As I said, it takes all the numbers, puts them into 0 and 1 in the following way. The 0 goes to 0.5. High numbers, like 5, go to closer to 1. Low numbers, like big negative numbers, like -10, go to something closer to 0. I think of it as a magnifying glass, because I just kind of, when I see the magnifying glass, I'm like, the world kind of just goes in a little interval. I don't know, it's just in my head. But if you like math, the formula is one of the formulas of activation function is 1 over 1 plus e to the minus x. You can see it on the right here. For large numbers, 1 over 1 plus e to the minus x is almost 1. For small numbers, it's almost 0. This is the one we use now. That step function is the one we used before, which says yes or no. And so once we apply this to all those numbers, we get our probability function. Okay? And now we're going to use probability to find our error function. So let's look at these 4 points, and let's look at a model that tries to split them. Now this is kind of doing a terrible job, because it thinks of the red point over there, it thinks it's blue, and the blue point over there thinks it's red. So it's a bad model. Now, how do we tell that this is a bad model from the probability perspective? The way we do it by saying, this thing is very unlikely to happen. So how do we quantify how unlikely to happen something is? Well, the probability model gives me some probabilities, right? These are the probabilities. The point that's way over there has a large probability of being blue, all the way here until the point here has a low probability. Can you see the numbers, or is it just kind of blue over blue? This one says P blue goes 0.9, 0.6, 0.3, and 0.2. So what's the probability of being red? Well, it's just 1 minus that. So 0.1, 0.4, 0.7, and 0.8. And what's the probability of this entire arrangement happening? Well, let's look at the probability of each point being the color they are. And if we assume that these are independent events, then the probability of the whole thing is equal to the product of the probabilities. So given this model, these points have these colors with a probability of the product of 0.1, 0.6, 0.7, 0.2, which is 0.0084. So it's very unlikely. That's how we can tell that this model is bad. Let me repeat that. We have this over here. And now, if we could only maximize probabilities, if we could only just take steps to make this probability better. Now we have a much better model because this model has 2 red points in the red area and 2 blue points in the blue area. Again, this model gives us probability. So let's say the probabilities that it gives us are 0.8 and 0.6 for those 2 being red and 0.7, 0.9 for these 2 being blue. And if we find the probability of this arrangement, we multiply them, and we get 0.3024. So it's 30% likely that these colors are the colors that they are over there. And that's much, much more likely. So that's how we can tell that the second model is better than the first one, because the points are more likely to happen in those colors. This is called maximum likelihood. Okay? But now, how do we maximize probabilities? Like, how do we take these numbers and turn the 0.0084 into a 0.3024? There's a problem here, and this that we have products, and I hate products. Product of 4 numbers doesn't seem so bad, but if you had 1 million data points, how does the product of 1 million points, 1 million numbers, all between 0 and 1, how would it look? Like 0.0000, right? It would be tiny, and not only tiny, but volatile, because if you take one of the factors and change it, the whole thing changes like crazy. So products, not good. What's good? Sums are good, right? So why don't we turn these products into sums in order to use them properly? So another quiz. What function can we use to make our products into sums? Sine, cosine, logarithm, or exponential? Thank you. You guys are awesome. Yes, logarithm, because logarithm of a times b is logarithm of a plus logarithm of b. So let's use the logarithm to turn our products into sums. Here I have my bad model on the left and my good model on the right. Here I have my probabilities and the product of them. And I'm going to turn this magically into sums by applying the logarithm. Now, I apply the negative logarithm. Doesn't matter. Like, I just minused it, because if you have the logarithm of a small number, it's a negative number. So I minused it to get positive numbers. And what do we get? What if we actually associate each point with the logarithm of its probability? Okay, what do we get? Take a look at this. The sum of the negative logarithms is 4.8 for the left one and 1.2 for the right one. So it's a big one. It's a big one for the right. It's a logarithm of a small number, and a small one for a big one for that one, and a smaller one for this one. So it can be considered an error function, right? And if we associate each of these logarithms with the point where it came from, that's it. That's an error function, right? That actually helps us. And if we calculate the values, we can see that points that are correctly classified, like this one, has a small error of like 0.1, and points that are incorrectly classified, like that 2.3 over there, has a big error. So there it is. That's our error function. It's the logarithm of the probability of the point being that color, and the probability is the sigmoid of a linear function. So the error is negative logarithm of sigmoid of linear function. The last? Yeah, sure. So we want an error function, right? We want something that's big if you're misclassified and small if you're correctly classified. So we have a linear function, right, that gives us the blueness of every point. We crunch it with a sigmoid, so that now the blueness is between 0 and 1. Okay? And now, for wherever the point is, there's a probability of that point being the color it is, right? Which is high if you're correctly classified, whatever you are, or low. So we take the logarithm of that number, and that answer we get is the error function. So that's actually a magical number that is big when you are when you're misclassified, and small if you're correctly classified. It actually works out that if you're correctly classified, this number is almost 0. And if you're incorrectly classified, if you actually combine the functions, it's actually almost a linear function on your distance from this. Yeah. So you can actually think of error as distance from the line if you're misclassified, and 0 if you're correctly classified. And that gives you perceptron algorithm. If you think of it in this continuous way, it gives you logistic regression. Okay? So far so good, or any questions? Okay, so let me ask you a very loaded question. Is data always nice and linear? I can see all of you shaking your heads going, oh, no, it's not, right? For example, here's an example. The acceptance at a university, okay? The same problem as before. Let's say we have the student. Student 4 who got grades, test 9 and grades equals 1. Do we accept that student? Well, based on the model, we should, because they're over the line. But maybe we have a model that says, you know what, if they did too poorly on the grades, maybe they copied in the exam. I don't know, something like that. Let's just say our data doesn't look like that, and it looks more like this. This is more realistic. So these points are red. We have a sort of a minimum on the grades and a minimum on the test. So this is more realistic, but it's not linear, unfortunately. So we need a more complex model. So what's next after a line? What's the next thing? What's more complex than a line? I don't know, we can have, yeah, exactly, a circle. We can have 2 lines. We can have a curve. So all these are different algorithms that give you different solution regions. But we're talking about neural networks. So neural networks will give you sort of either 2 lines or this curve. Let's go for this curve. Let me show you how to get this curve, and we're going to get it as a combination of the linear models from before. So basically, and how do we solve it? We solve everything with gradient descent. All these just a slightly more complicated thing, but you always take the error function and start minimizing it until you're done. So nonlinear regions, basically what we want is something like this. A probability function that in the black line is kind of like 50-50 for being blue and red, and well into the blue area gets closer and closer to 1, and then into the red areas gets closer and closer to 0. That's what we want. That's the probability model that we want. And how can we build it? Well, we have already some of them, right? We have the linear ones. So for example, what we're going to do is we're going to combine these two to obtain the other one. Like this, we overimpose them. And then magic. That's how we're going to get them. Okay? Let me be more formal. Basically, what we want is sort of a world in which you can add these two and get the third one. Right? So let me show you how to do it. These two are probability distributions. So if I pick a random point in the plane, each one of them will tell me what's the probability of being blue. So let's say for this point over here, the model on the top tells me 0.7 probability of being blue. And for the same point, the model on the bottom says 0.8 probability of being blue. So what should be the probability on the resulting model? On the resulting, anybody has an idea how to combine two numbers? 0.7. Oh, that's good. Yeah, no, that's not. But it's a good, like the average, right? Yeah, that's pretty good. But we won't take the average. We'll actually take naively. Maximum is good too. They're great ideas actually. They should all see if they work. We're actually going to take the sum. 1.5. Is that a probability? No. How do we turn it into a probability? Log, almost, yeah, the sigmoid function, actually. We have a function that takes all the numbers and crunches them into the interval 0, 1. So we can use it, right? We might as well. So we use our sigmoid function. That's an image of the sigmoid function, which actually says sigmoid of 1.5 is 0.82. And so after adding every single probability on the models and applying sigmoid, we get this region. Okay? Now, what if I want to? I can do even more than just adding them, right? I can take linear combinations of it. What if I wanted, say, the top region to have a lot more of a say than the bottom region? Okay. I want the resulting child to look a lot more like the one on the top, like the one in the bottom, right? So what do? Well, we can just add constants, right? We can say I want 7 times the first one plus the second one equals that. And I can even add biases. I can even add, like linear combinations are the first one times something plus the second one times something plus a bias. I can add a bias, right? I can say if I have 7 times the first one plus 5 times the second one, then the resulting is just 7 times 0.7 plus 5 times some 0.8, and I can add a bias like -6, for example, and say -6. So like pure linear combinations, the way you create a line, right? A linear combination of two variables to get a third. This is how you create regions, a linear combination of two variables, of two regions to create a third one. So if we get this 7 times 0.7 plus 5 times 0.8 minus 6, that's 2.9. We apply our sigmoid function and get 0.95. Okay? So that's how we do it. That's how we combine regions into more complicated regions. So let me actually show you how do we sort of draw this in a neural network. This is how we draw it. If we have 7 times the first plus 5 times the bottom minus 6, we put it in a node like this. And now nodes can, a line can also look like a node. If I have this region, this probability distribution, where the line that cuts it is, for example, 2x plus 7y equals 4, I can also express this as a node like this by just putting the coefficients in the edges. Okay? So I can just take those nodes and join them, and that's how I create neural networks. And why is it called neural networks? Because this kind of looks like a neuron where if I take the point x, y, and this outputs the probability that it's blue, then if I take a brain cell, then you have nervous impulses coming from the dendrites and something coming out from the axon. So basically that's the source for to model how a brain operates. So let me show you how to join them. We have the first line, let's say it has equation 5x minus 2y equals minus 8, and we put it in that node over there. Then I have another one with equation, for example, 7x minus 3y equals 1, and we put it in the bottom. And now we join them by saying I want 7 times the top one plus 5 times the bottom one minus 6. And then the magic happens here. Check it out. There. That's that's a neural network. If we clean it up, we get this. Okay? So when you think of a neural, and we write the coefficients in that way, right? The nodes on the top give us the top region, the nodes on the bottom give us this one, and the ones on the very right tells us how to combine them. So whenever you think of a neural network, it's good to think about what the region in the plane or in higher dimensional space that bounds. Okay? Yes? How's that different from ensemble models? Correct me if I'm wrong, but that's kind of like when you take two models, existing models, and boost them to get something better. Well, in here we're still building our model, so this is part of our training. So we're basically building our entire model and then training it at the very end. So whereas when you're boosting, you have some existing models and use them to, like, you train them, see what your error is, then use the other one on top. So these are more like iterative. This one's like one thing, but they both have the same sort of concept, right? Yeah. Yeah, I can share the slides. Yeah. So this is how I see neural networks then. It has input layer, hidden layer, and output layer. The input layer is the variables coming in. Sorry, I should have put x, y, x1, x2, but the layers coming in. The middle layer is just a bunch of linear models, and the output layer is just how to combine these output models. We can increase this, we can make this more complex, right? If I make the middle layer larger, for example, if I have 3 things in my hidden layer, I can actually make more complex things like this, like bound this area, this triangle. As a matter of fact, there's a result that says that if you, with only making the middle layer as large as possible, you can actually approximate any function. What if I have the first layer is bigger? What if the first layer is bigger? Well, then I have just a higher dimensional thing, right? Now I have three variables coming in, so I live in 3 space. My hidden layer is just a bunch of planes in 3 space, and my output layer just combines these planes into regions. What if I make the last layer bigger? So if I make the last layer bigger, I have different ways to combine these areas to get different solutions, and that's when I want to do multi-class classification. So for example, if I want a model that tells me something is a dog or a cat or a bird, that's how I do it. This works a lot in image recognition, right? The beginning of the neural network gets sort of basic things about the image, and the final layer is the one that says you're this, you're that, kind of puts them together. But the power of neural networks really comes in when I put more hidden layers. So I can stack as many of these as I want, My first one's going to be linear models. My second is going to be like slightly more complex models that are combinations of linear models. And I can go as far as I want. This one combines these two. And the beauty of neural networks really comes when you stack many of those. So when I think of a neural network like this, I try not to think of it as this bunch of nodes, but I wonder if there's some bounded area in high space that gets bounded by that. And so now when I look at neural networks, they're a little less scary, right? Like this is self-driving car, for example. Actually, the real one has more, but it basically takes your input as pixels, turns it into a vector, saying if you're white, you're 1, you're white, and you're black, you're 0, or somewhere in between, and then just feeds it in, and then goes through hidden layers, and then at the end you get a multi-class classification that says, okay, your probability of turning left is 0.9 and turning right is 0.01, so turn left, stuff like that. And if you think of the one for playing Go, it's the same, right? It just takes the board, turns into a vector, inputs it in, bunch of layers, and at the end it gives you some classification of whatever number is bigger here is the move you should be making. But now the question, and the question of last thing is how to train the neural networks, right? Because we want to, these models are pretty, but we want to find the perfect model, right? So we want to do is what we did with the linear one, but on steroids, okay? So in a nutshell, this is what happens. You have your neural network with a bunch of parameters, and that gives you some boundary, right? So we use gradient descent. We start with a random model. So we start with random numbers on the edges and nodes, and that gives us this bad region, which means we have a large error, so we're on top of Mount Everest. And we take steps to make it better and better, to reduce our error, until we descend the mountain and we get like a perfect solution or a pretty good solution. But let me be more specific. So this process is called feed forward. You take your two variables. Okay, you put them in your model. Your model now, this is the only equation. I'll use W. It's a linear model with weights W1, X1 plus W2, X2 plus B, which go on the edges and the bias. And then you plot your point, and the model tells you what was the probability of the point being blue, right? Now, how do I go backwards? What does the point want? The point wants, the point says, okay, remember from the beginning, right? I want the line to move in this direction towards me, okay? How do you move in that direction? Well, you have to update the linear equation. So you update these two weights. So this tells the lines, for example, this is not a realistic example, but basically it tells, okay, I want W1 to go lower and W2 to go higher. And if you do that, I get new weights. That gives me a better linear model. Correct? Now, what about multilayer perceptrons? What about neural networks? How do I do this? Well, now it's a different error function, right? It's a more complex error function, so we're not in Mount Everest anymore. We're in Mount Kilimanjaro. Sorry. And we want to do the same thing. We want to take the gradient of the error function and manage to descend to the bottom. So let me recall how's the full process. The full process is you plot yourself in the top and the bottom, then you combine these two models, and you plot the point, and that gives you a probability. Now let's go backwards. So this is sort of where the meat of the backpropagation happens. This point on the right is misclassified. So it says, I have a big error. I need this model to decrease my error. So I kind of want you to move in this direction. It wants this blue region to move in the direction of the point. Now, how do we tell the region to move in the direction of the points? We look at the previous layer. Which of these two models is classifying the point better? Who votes for the top? Who votes for the bottom? You guys are awesome. The bottom one misclassifies a lot better. So we kind of want to listen to the bottom model a lot more than the top model. So we decrease this weight and increase this weight, right? So let's do that. Let's tell the model to decrease this weight and to increase this weight. Yes?
So there were both weights and then these constant factors as well.
I kind of forgot about the constant factor because it's not pretty graphically, but yes, think about a constant factor too.
Are they getting adjusted as well?
Yes. Thank you for the clarification. Yes, there is a constant factor too that gets adjusted. Imagine it in the background getting adjusted. Thanks.
Can you comment on how it gets adjusted? Because this I can sort of get your explanation. It's great.
Yeah.
What do you do with the constant?
I mean, at the end of the day, you're taking a derivative, and the derivative gives you a derivative with respect to the first constant, to the second constant, and to the weight, and to the bias. So it tells you, if you adjust, I mean, if I adjust this, for example, let's say I subtract it, then the blue area is going to get bigger because all my probabilities are going to get smaller. And so the 50 region will move up to like, or maybe move up to here, right? So think of the B as like, if it's high, it just moves here, and if it's low, it just kind of moves down. Okay? But yeah, so these derivatives magically kind of tell you where to move, but graphically we can think of like they're actually just doing things to move your region more towards where you want it. And now let's actually go to the linear models and ask them what they want. So the top model wants the line to go closer or farther? Closer, right? And the bottom model wants it to go farther. So that also updates the weights in these linear models and the bias as well. I'm hiding it, but the bias as well. And it tells them, let's just say, move up, move down, and move up. Now this part is purely fictional. But imagine that it just tells them what to do. And this is backpropagation. When you hear backpropagation, this is what happened. You have your error, and it backpropagates all the way to the end, and it tells every weight how to change by taking the derivatives. And since this is a composition of function, the derivative is a product of derivatives. And each one will tell you how to update each weight. And so you do the process, you update the weights by a small amount, then you update the weights by another small amount, and then you get a better region. Okay? And that's it. That's backpropagation. Any questions? So yes, I totally cheated here. A linear equation is W1x1 plus W2x2 plus B, right? And the W1 and W2 make the slope change, because the slope is W2 minus W1, W2 divided by W1 negative. And the B makes it go up and down. So you have three ways to change these lines, by moving them like this or by up and down. And then you can also have three ways to combine these two models into the third one, right? By saying I want more of the first one, more of the second one, or like a higher bias, which makes it all more blue, or makes it all red if it's lower. So you have 9 parameters, right? And the backpropagation tells you how to upgrade each one of these parameters to a new set of parameters, right? Until you get a good solution. Okay? So any questions? Yeah. So to prepare you for Arpan's part, I'm going to actually put some math in here. This is how feed-forward works. I have my x2, x1, and my bias unit. Now I'm putting the bias unit as 1. And basically you have some matrices, right, with the weights of the edges. W1 for the first matrix, W2 for the second matrix. And then what you do is an operation on the matrices, right? And then sigmoid, and then operating of these, and then sigmoid to get your prediction y. Okay? This is a slightly larger example. You x, multiply by W1, apply sigmoid, multiply by W2, apply sigmoid, multiply by W3, apply sigmoid, and then you get your prediction y. So that's how feed-forward works, and that will get you ready for the visualizations on Arpan's talk. And I think that's all I have for now. And we can continue. Yeah, I'll do the presentation.
I asked Luis to keep up the slide because I wanted to quickly point something out. So when you look at the actual operations, the mathematical operations that are happening, it's basically, you have a vector of numbers, you're multiplying that times a vector of weights or a matrix of weights, and then you're applying some function and so on. So each of these operations is basically a matrix multiplication, right? And if you think of a large data set of a certain set of x values mapped to a certain y value, another set of x values mapped to another y value, each of these is a sample. And in your data set, you can have multiple samples, right? So you think of one sample has x1, x2, x10, all the feature values. gets multiplied by the weights, and progresses through, gives you one y value, right? But you can do this for multiple samples. And the great thing about matrices is you can expand that dimension and basically do multiple of these operations in one go. So now instead of having one vector of x's, you have a matrix where the way you can think of this as either orientation, but for instance, referring to this diagram, each column is one sample, and then you have multiple such columns of data that are being fed in. So that's where the idea of generalizing from a vector to a matrix to now if your samples themselves are multidimensional. So for instance, images. So you have basically a matrix that is being fed in. Now if you have multiple images that you want to put through, that's a three-dimensional array. Or in general, you call them tensors. And that's where the term tensor and TensorFlow comes from, because the unit that they use to represent all their data is a tensor. And that can have, so if it's a scalar, it's basically, it has 0 dimensions. If it's a linear array, then it has 1 dimension. If it's a matrix, then it has 2, and so forth. So I just wanted him to throw this up. I'll switch over to my computer. Thanks. So Luis asked earlier, a number of you have some experience with neural networks. I wanted to quickly check how many of you have used TensorFlow before. Okay, that's cool. It shouldn't be too hard for the problem that I'm going to illustrate, but it'll be great if you want to follow along with the talk. You can go to github.com/pythonworkshop/tensorboard demos. I'll leave that up for a second. So TensorFlow is a neural network deep learning library that Google released some time back. And it has this visualization tool called Tensorboard, with which you can look at the actual network structure, as well as log how errors or other values change while training and testing. So it's a really neat tool. Has anyone here used Tensorboard before? Cool. So this is going to be pretty basic, just an introduction to the tool. But you can follow this by bringing your own models and trying to apply Tensorboard to see what they look like. It also helps in debugging these models. All right. In the GitHub repo, there's an IPython notebook. You can open that and follow along. There are a few introductory slides. I'm going to skip them because Luis has already covered that. So there is, actually, let me go over this. If you don't have TensorFlow installed, there are instructions in that notebook as well. So these are just different diagrams. I think Luis's were prettier. But we ended up, and here's where I'm basically expanding those W matrices that we had. Like I was describing, you can have multiple examples being fed through the network at the same time. So this is sort of a general abstract picture of what a deep learning model looks like. You have some tensor that is being fed in, and there are some tensors in between that are being multiplied and added, and then you get a tensor out, right? Cool. So let's try to make a very simple model like this, a neural network model, and then we'll see how to visualize it using Tensorboard and what it actually looks like there. So I'm going to generate some random data, just some dummy data here. Can everybody see this fine? Might be a little hard for people at the back, but basically I'm creating random samples in two-dimensional space, and then labeling them as if x0 squared plus x1 is greater than or equal to 1, then I'm giving it a label of 1, otherwise 0. And let's look at some of those values. Just 2 features, and I'm showing 10 of those samples. And then their corresponding labels. And we can actually visualize this data. I'm plotting them, just scatter plotting them with matplotlib. And this is what it looks like. If you notice carefully, there is a curve because of the quadratic term. Cool. Now we have that entire data set. This is basic machine learning. We split it into 2 sets, 2 groups, one for training, one for testing. And I'm specifying test size as 300, and initially I had like 1,000 total samples. So I get 700 training and 300 testing samples. If I visualize the training set, it kind of looks like the original set. Similarly for the test set, but it's sparser because we have fewer samples. All right, now this is where we start with TensorFlow. And just to recap how you create a TensorFlow model, importing TensorFlow as TF. We're initializing a session. Now TensorFlow uses a session to keep track of all the variables and operations that occur. So you kind of have to initialize this typically before you define any of the other operations. Then what happens is whenever you start defining the different computations, it starts adding them to that common session graph. And we'll see what that graph looks like using Tensorboard. So the first 2 items that we define are a placeholder for X and a placeholder for Y. These are placeholders because we're going to feed them data while training and testing. So they're not actual. So you can think of them as variables, but they are special in the sense that they can be loaded with data. And I'm defining the size based on the number of features. My output size is just 1 because I just want a single label, 1 or 0. Then here's where we create the neural network. I'm going to define some convenience functions. So the linear function, and this is where you can see all the math being translated into code. You take the size of the input layer, the layer that this is going to connect to, and then you define a set of weights and biases, and then you define the operation as input tensor multiplied by weights. That's what matmul does, matrix multiplication. You multiply them, and then you add the biases. So this is slightly different from the entire sort of matrix approach where you included the bias term in that matrix itself. This is 2 separate operations, but it amounts to the same thing. Now, you might have noticed that I'm supplying these names called weights, biases, multiply, and add. These are things that will end up showing in the Tensorboard visualization. That's why I'm explicitly naming them. Otherwise, the system might assign some sort of auto-generated labels like op1, op2, op3. This is much more useful. Okay, so this is a convenience function I've created to design linear layers. Now I can just call them as many times as I need to create my layers. Now, I can also define, so this is basically showing that if I use that linear function and no separate activation function, then this is what the output would look like. But for neural networks, to add some non-linearity, we want some activation functions. So this is where I'm defining, again, convenience functions to apply those activations. And it's basically the sigmoid layer is basically linear layer and then apply the sigmoid function on top of that. And this is a small visualization to show you what the activation function looks like. Similarly, we have a few other activation functions. One is ReLU. So in this network, I'll basically use a combination of sigmoid and ReLUs, which is regularized linear units. So remember, those were just functions, convenience functions we defined. Now we basically call them to create our layers. I'll create one hidden layer with 10 units, and then another hidden layer with 3 units, and then an output layer with 1 unit. Okay? And this is just up to us. I just arbitrarily picked this structure. Again, notice that I'm defining these scopes. tf.name scope hidden 1. This is not something that you have to do, but it again helps in visualization. It gives anything that you define within that scope, it gives this as a prefix. So when we look at the visualization, you'll see these strings as grouped together under hidden 1, hidden 2, and output. Yeah?
Just to correlate with what you told, right, from that correlation. So let's say, so the whole intention of the exercise is to have a model wherein we can sort of minimize the error function from splitting my input points, right?
Yeah.
Right. So the activation function of which we are is something which we provide. And it is model specific. I mean, how do we decide that? For example, I mean, I have some samples there. I have 1,000 bonds, right?
Right.
I don't know, I have to leave a hidden layer and I provide activation function.
So you're basically asking, like, there are a lot of choice points, a lot of design decisions here. And this is basically an engineering exercise. Like, you have some guidelines, you have some heuristics you can use to figure out how many nodes you might want, primarily based on your data, like, how many features or what the input size of your data is, and the complexity of the data. So you can do some initial analysis to see if those variables, many of those variables are correlated, then you might not need as many hidden units. If there's a lot of variance in them, then you might need a lot more hidden units, but there is a lot of experimentation involved. As far as the activation functions are concerned, one simple heuristic you use is what's the end result you want. So if your end result is like a label 0 or 1, then you want something like sigmoid or tan H, which would be -1 and +1, depending on the nature of the output you need. You use RailUse because it's going into fairly advanced topics here, but you use these different activation functions to resolve issues that might come up during training. So RailUse, for instance, avoid the problem of vanishing gradients. But there are other sort of heuristics and sort of guidelines you can use to choose what activation functions to use. And sure. And at this point, we've only defined the network. We haven't defined the loss function yet. We haven't gone to the training part yet, but we'll come to that. Just keep this idea in mind. Like, we had an X placeholder. If you look at how it's called, we're passing in the X placeholder as the input to the first hidden layer, and then we're passing in hidden 1 as the input to the next hidden layer, and then that to the output layer. Cool. Now we choose our error metric, and again I define a convenience function. You could just directly call the body of the function as well. First I convert the labels, which were integers, to float. Then I subtract so the logits are the predictions from the model, logits minus labels, right? And then I compute the L2 norm, or the Euclidean norm of that vector. And all of these things I'm doing using tf.nn.l2loss for a reason, because when I define this as sort of the forward pathway of how to do these computations, TensorFlow internally computes the derivatives based on these functions as well. So that's another nice thing about using TensorFlow or some neural network library like this. You basically lay out how you want the forward pass to proceed, and the library should ideally internally compute derivatives that it needs to carry out backpropagation. So again, I call that convenience function to define L2 loss within a scope that I'm calling error. And you'll see this in the visualization that error node shows up as error/L2 loss, or it will be grouped under the word error. And it's basically the difference between the output and the Y placeholder, which is the actual ground truth labels. Another thing I added at the very end is tf.summary.scalar. So it's used to basically log these values. So when we go through training, then each of these error values at each iteration will be logged. And we'll see what this looks like. It'll become clearer soon. So then I quickly print out what the computation graph currently looks like. It's messy to see in text, but it'll be prettier in the visualization. And then I initialize the logging mechanism, which is how Tensorboard gets all the data to visualize. You don't need to pay attention here. It's just a bunch of administrative things you need to do. Cool. Then we start training our model. This is a function I'm defining, and it's, all of these optimizing functions are defined in TensorFlow, so you don't have to do a whole lot of work. I basically chose gradient descent optimizer. I passed in a learning rate parameter, and then I defined the training operation as train based on this error. Okay, so it'll try to reduce that error. Now I define some more training related parameters, like the number of iterations I wanted to go for, and how many samples I want to feed in per iteration, right? These are again TensorFlow steps. If they're not familiar to you, these are just things you got to do to make TensorFlow run. And then here's where I run through all the training iterations. So for step in, range, num steps, I sample based on a batch size. I create a feed dict. It's again a very TensorFlow specific thing. I show what is the mapping for these X placeholders and Y placeholders that I created before. So I'm saying put these training samples in X placeholder, put these ground truth labels in Y placeholder, and then feed that in through the training algorithm, run it for one step. I'm going to time it, how long it takes as well. And then every 100 steps, I'm going to print out what the current training error is. And this is the output you would see if you ran this block of code. Notice that as part of every 100 steps, I'm also running all the summaries. This is where the actual logging happens. So I defined what items to log before, and then this step is where I'm actually logging them to file. So this is the overall sort of training step. Now at the end of this, I have some model that has been trained. Now I want to test my model. So remember, we split the data set into training and testing. We kept the test set aside, so we'll see how it performs on the test set. Same operation, we replace the X placeholder and Y placeholder with X test and Y test values. And then we try to predict what the labels are. And here, if I plot them, you can see it does misclassify some of the points. I've put circles on those, black circles. And you can see that they're closer to the line of separation, which kind of makes sense. Like it estimated some boundary, but some of the points were misclassified. And the test error, the L2 loss that we computed is 2.93. That's not in any particular range. It's just the loss it was trying to minimize. Cool. Now, after having run through the training and testing phases, the TensorFlow session has generated a log file, or actually a collection of files. What you can do is go back to your terminal, and from whatever directory you were running this code in, you can actually, when I configured the logging, I said put the log files in this logs directory, and you can run the Tensorboard application. The Tensorboard also runs like a web server. So it runs in the background, and then you can open up this link. It's typically on port 6006, 6006, and you can see what it looks like. I have a static visual. So this is what the computation graph would look like. And you can expand on each of these nodes to look at the operations. I'll come back to this. And this is what the error plot would look like for the loss that we were logging. Now, instead of doing this here, let's actually switch to Tensorboard and see if that's running. Okay. So when you open up Tensorboard, this is what you would typically see. There are multiple different items that you can visualize. The thing that I typically start with is the graph, and this is an interactive visualization. So remember all the naming that we did, hidden 1, hidden 2, output, and error. This is where they show up. And you can double click any of these. It opens them. Right? You can zoom in to see what's going on. So this is X. That's the X placeholder. Whenever you feed in data, this is where it comes in. And within the hidden layer, there are a set of weights. This truncated normal is a way to initialize these weights. This is just there in the site. But basically what's happening is we're multiplying weights times X, and then we're adding in the bias, right? And then we're passing that through a ReLU function, and then that's the output for this hidden layer. So it makes it really easy for you to quickly analyze what your network structure looks like. If there are any mistakes you've made, they're much easier to catch here. Another thing that this visualization does is, if you zoom into these links, it'll show the shape of the tensor being fed in, right? So why is there a question mark here? Because it's a placeholder. You can put in as many rows or samples of data as you want, times 2 columns for the 2 features. This will depend on the dimensionality of your feature, right? That's going in. Your weights are 2 cross 10. The resulting values are whatever number of samples you fed in times 10 columns. And then you add in the biases. And so at each step you can see how the shape of the operation you're carrying out, how it changes the shape of the data as the data moves through the network, right? And you can see what the output of this overall hidden layer is. Cool. So the second hidden layer had 3 units, I think. Right. So now when you have these weights, the size of the weight matrix is 10 times 3. If you work it out in your head, how matrix multiplication works, it will transform this 10-column input into 3-column output, right? And so basically, from the hidden 2 layer, you get 3 values for each sample, right? That goes into the output layer. This output layer is also interesting. It's a little different from the previous ones in that we have a sigmoid function instead of ReLU. Okay. And lastly, even the error node has some more detail to look at. So remember, we took the y's, which are the ground truth labels 0 or 1, converted them to float. Then we're subtracting that from the predictions, right? And we're computing the L2 loss, or the Euclidean norm of that. And this icon here kind of signifies that this loss is being logged. So now we can go ahead and look at this log. It will be under our scalars. Remember, we named the overall scope error. That's what we see here. And this is the L2 loss. So right now, by default, there's a TensorFlow is smoothing the loss. Let me reduce the smoothing parameter. And you can see this is the raw loss value at each. I was logging every 100 iterations. So this is how the loss reduces as the training goes on. Now, if you had a separate validation set, then what you could do is log the values for the training and the validation set and you can analyze the complexity curves or the learning curve changing as you're going training through time. So yeah, these are just two things that I typically use when I'm training a neural network model. These error values are pretty a good signal, a solid signal to use to see whether your model is performing as you're thinking or not. Sometimes you'll basically have the error value flattening out and or maybe just wavering around the same point. That means it's not really getting anywhere. Another thing that you can visualize with Tensorboard are the actual weights. So think of all the weights in the network or all the weights in one layer. You can basically plot them as either as a histogram or as a sort of distribution just scattered, and then you can see how they're changing over time. Typically what you'll see is, if you start with a certain randomly initialized set of weights, they will sort of spread out as you train them because they're learning the features of the data. But if they don't change a whole lot, or if they change but they become correlated in one sense, then you can figure out that there's something wrong going on in the training procedure, and you can debug your model based on, or your training procedure based on that. Cool. So that's pretty much all I had for the presentation. But what I wanted you to do is, if you go into the repo, I'll leave this up. You can try this for yourself. You can open the notebook using Jupyter. There are instructions there. You can run the model. You can open Tensorboard and see what the visualization is like. That's something that you can already do. But what would be really cool is, especially for those of you who have tried your hand at neural networks or TensorFlow before, take your own model, right? Your training pipeline, and add in these logging mechanisms and this naming scheme, and then visualize that model and see what it looks like. I've gone with a very simple model, 2 hidden layers, 1 output layer, but you might have used something complex like a convolutional neural net or a recurrent neural net, and it'll be a lot of fun for you to then go back and visualize it. So if you go ahead and do that, what I would encourage you to do is maybe take a snapshot and share the graph visualization with others, either on Twitter or somewhere else. And we have 5 minutes now, so maybe we can do questions now, and we can, we'll be around here, so you can ask us anything later as well.
Thank you, Luis and Arpan, for the session. We're going to have a Q&A session for next 10 minutes. So if anybody has any questions, they can probably ask now. I'll be moving around with the mic, so if anybody needs mic, just let me know.
It's too big?
No, just go.
Oh, you go.
Thank you. Great overview of lots and lots of things that you guys squeezed in. Ooh. So here's my question. Oh gosh, I don't know how to do this without squeaking. Closer? Okay, all right. So here's my question. The people that I know who use deep learning, much more than I do, mostly are using it for image recognition and computer vision use cases. So I was wondering if you could talk about what the advantages are of using TensorFlow and deep neural networks over, say, more traditional artificial neural networks and backward propagation. Is it that with the tensors you're using n-dimensional data instead of just 2-dimensional data, or are there other main advantages you can use this with beyond computer vision and machine vision sort of use cases?
Sure. Do you want to? So keep this right. So one of the things is, just to clear out the myth, deep learning or deep neural networks are exactly the same as regular neural networks. The idea is just over the past maybe a decade or maybe at least the last 5 or 6 years, we've seen the number of layers in the neural network grow a lot. And so we've started calling that deep neural networks and deep learning, but it's no different from the same neural networks we had before. One of the reasons they weren't as successful before is because we weren't able to perform the computations at that kind of scale. Another reason was we didn't have as much data around to train these neural networks. So whenever you grow a neural network in size, you're basically growing the number of parameters you have to train, so you need more data, more computation power, right? One of the reasons these neural networks are suitable for a lot of like image recognition and other high-dimensional data applications is because when you define a neural network, your features don't really have to have any meaning associated with them. So when you throw images at a neural network, it treats either in each individual pixel or each individual region as a feature, and it just runs with it, right? And so it's really easy to throw this data in without having to think about like what these features mean, and you just define an appropriate loss function or metric that you want to optimize and statistically optimize that whole thing. When you have other forms of data, for instance, like records records for loan approval or for admissions, etc., that you want to analyze, those columns or those features that you have actually carry some meaning. And if you throw that data into a neural network, it will probably do a good job of like classifying or predicting things, but then you start losing the meaning of those variables as it goes through. So when the neural network says that, okay, admit this student but don't admit that student, it'll be harder to say why it is so, what features is it looking at. But to answer your question, they can be applied in a lot of different contexts. You just have to find the right way to transform your data into a numeric or a vector representation. That's pretty much it.
Just following up on that question, if you have highly categorical data, and will the deep learning neural network still get a great prediction or a good prediction, even though you don't know what's driving that category or what specific category is driving it?
So when you say category, you mean versus numerical data? Like if my input is a number, or if my input is a yes or a no, or like, normally what you do is you turn those into numbers. So if my input is, for example, dog, cat, bird, then I make 3 columns, and the one for dog is like 1 if it's a dog and 0 if it's not, and then the one for cat is 1 or not. So you normally want to turn everything into numbers. That's called one-hot encoding. And then that's how you input into a neural network. And then what was the second part of your question?
If it's highly categorical, like you have all these non-numerical scale values like dog, cat, bird, things like that, do you lose that? Like how performing is it in neural network?
Yeah, it still performs well, but yeah, the thing you do is turn them into numbers. So if you have something with 10 categories, unfortunately, you just now need to add 10 dimensions of data and things of points of coordinates 1, 0, 0, etc. So it makes it harder, but it's still doable. You want to add something? Yes.
So can you say anything about issues with overtraining or overfitting, which at least used to be a big problem for neural networks? And is there any additional challenges when you're using a tensor model as opposed to the old way they used to do it? Are there any tricks to getting around it?
So just to point that out again, the tensor model is just another way of looking at it. It's doing exactly the same thing as before.
It's not batching them up in any way?
It is.
But it's the same?
Yeah, it is equivalent to what we've been doing with neural networks before. It's just optimizing for it using numerical libraries that can basically carry out multiple operations parallelly at the same time. But to your question about like overfitting, that has been a huge problem in neural networks. So if you think about it, a neural network with, say, a layer of like 100 nodes or 100 nodes for one layer, 100 nodes for another layer has like 200 parameters. And if the problem that you're trying to address doesn't need that many parameters, then your parameters will end up fitting too much to the training set that you have, right? So you have too many parameters. Now, what people have done is they've applied they've come up with a few different techniques to basically reduce the effective dimensionality of the parameters. So say you can have 100 different parameters, but if you put some constraints on it, how these parameters can or cannot change, then the effective dimensionality can be reduced. One of those ways is by using regularization. And one example of regularization is basically, in addition to the error loss, you add another term saying that I don't want my parameters to be I don't want the total sum of the parameters to be beyond a certain limit. Or if it is beyond a certain limit, then penalize that. So what happens is the parameters that you have, if they have to change beyond a certain limit, they must produce at least that much improvement in predictive power. Otherwise, they're not going to move more. And one of these regularizers is called the lasso regression, or the lasso regularizer. You think of it as putting a lasso on your set of coefficients. So although you have a lot of parameters, they're sort of tied down in a certain way. And that helps prevent overfitting. Now your parameters are not only optimizing for the training set, but they become slightly more generalizable. And there are other techniques that people have come up with, and I actually feel like these techniques, they don't get spoken about a lot, but these are the innovations that are powering deep learning right now. Because you can think of more data will always keep coming in. We'll always keep getting better at doing computations. But these are the techniques that are actually enabling sort of complex neural network models to be learned.
Learning more about using neural networks to find features in the data. If you have any kind of guidance or suggestions about which network to set up, or how to investigate the network, conceptually how to approach this?
Well, let me see. Normally, when it's like a one layer, like a linear model, you find features very easily, right? Because you look at which ones have a high weight, and those are the most, like if you look at which ones, then that means that's the one that inputs the most into your model and tells the most. Yeah, exactly. Once you get to several layers, it's hard to tell. Things like convolutional neural networks, for example, you can tell that certain layers are capturing certain parts of the image, like it's like an edge here, like an eyes, or the convolutional neural networks, they basically recognize images, but the way you do it is you don't run the entire. It's not fully connected, so you don't take the entire image and feed it in a vector. You take like little pieces and feed them so that if you have an image here or here, it's the same thing. And then you do that in several layers, and you start noticing that each one captures certain things. So if you're recognizing faces, for example, the first layer recognizes like dots and lines, the second one like eyes and noses, the third one like puts them together face. So in that one you can tell features. I don't know if you want to add anything about other neural networks that capture features.
I think so. Like the basic idea is, yes, looking at the weights and what the ones that are higher are basically that much more effect they're having on the end result. Another thing you could do is do some sort of automated ablation study. So you leave out one feature, train a network, leave out one other feature, train a network, and you can actually put it in an automated pipeline, and then you get all those results and figure out which model worked best. A variation of this is actually something that neural networks use internally. It's called dropout, where instead of training on all of the inputs at every stage, you randomly leave out some of the connections. You basically set those connections to zero, those weights to zero. What this does is it builds more versatility in the system. So the ultimate result is no longer dependent on specific pathways, because you've basically closed that off and trained once, and then you randomly close some other pathways and you train them. I think with neural networks, the approach has become basically throw as much data as you want, throw as many features as you want, and let the network figure out what it needs and what features to pay attention to.
One question from here.
All right, thank you. I got a very basic question. Like, I'm a traditional image processing guy and also traditional neural network user. So I understand that I can use this Excel file, put the row, and each row is our, let's say, training, like entity or record. In terms of segmentation using deep neural network, let's say I'm feeding one column, right, at a time. And to me, one column doesn't mean anything if I want to segment or if I want to understand the feature, right? So could you please give me some insights, like how it works? Like you can feed the entire image, and at the end we can segment our object of interest, or we can learn the features. Just a basic overview would be really appreciated. Thank you.
Sure. So again, going back to the idea of, let me actually put up the slide so it's easier. If you think of a deep neural network as a sequence of layers, then those layers can basically represent any piece of data, right? So for instance here, X doesn't need to be a single column. It can be an entire image. It can be a matrix. For, if you have volumetric data, for instance, from MRIs and stuff, you can feed in an entire 3D image, and that is one sample. And you can have many such samples as well. Computer doesn't care. It's harder for us to think of and visualize data in 4 dimensions and stuff, but it's just a tensor for the computer. And basically your dimensionality at each stage increases there. But as far as images are concerned, you can definitely pass in an entire image. To address the specific problem of segmentation, so one way of doing segmentation is basically you want to predict a label for each pixel in the image, right? That's one way of thinking about segmentation. So this group of pixels will all get 1, 1, 1, 1, 1 label. That's one component. 2, 2, 2, 2, 2, 2, 2. This is another component. So if you formulate it that way, then your input dimensionality is the size of the image. Your output dimensionality is also the size of the image. Or another way of thinking about it is size of the image times the number of labels that you have, the number of segments that you want. And yes, you can design neural networks like that. What you end up doing is you do a bunch of convolutions that capture the patterns in the data, and then you perform a series of deconvolutions that take whatever it has learned back to the size of the image. And the output you get, you can basically then interpret it as, okay, it's giving me high probability that this is labeled 2, this pixel is labeled 2, this pixel is labeled 3, and so on, and you can create a segmentation out of that. So, and the way you would train such a network is you would put in the source image, you would put in your hand labeled segmentation, and then you define an error metric based on the difference between those two, and back propagate the errors. So the process remains the same, the architecture becomes more complicated. Were you going to ask something else?
I just wanted to add my understanding. So we are really not giving the input as a column, we are rather giving row times column as one array and then fit this one, right? Or
Yeah.
case, and then we are doing each of these cases.
Exactly, yeah. So the input, the simplest form of input is a single number, right? But then you can have multiple features for each sample, so you think of that as a column or a vector being fed in. But for images, it's a matrix. For three-dimensional data, it's a tensor by itself, and so on.
So each pixel is going to each of them as it is.
Yeah, each pixel goes in as it is. You can also perform some initial sort of transformations or filtering or something else and feed the results of that as well. That's fine.
Is there a
one more.
Yeah, I was just wondering, I understand your expectation about propagation, but when I read about RNNs, there's this idea of memory.
Yeah.
How does that differ from the back propagation that happens in a traditional?
Yeah, well, good question. The difference is really more in the feed-forward process. Like a neural network just takes an input and gives an output. But sometimes you need the previous input. Like if you're generating sentences or something, the same word won't have the same effect all the time. So you actually need to remember what the last word was, for example. Or in like predicting stock, you need to remember what yesterday's price was. So you actually, the network needs to have memory. So what you do in a recurrent neural network is you take your input, get an output, but then part of your output is also feeds back in. So your input is kind of like a combination of whatever your input is today, or plus what came out last time. And so that way the network sort of remembers, and that way it can handle things like sequential data. As for training, then you use a backpropagation algorithm that is slightly similar to the current backpropagation, plus some extra gravy coming from the feeding back the output. But the concept is the same.
And so it's the memory of my last state in the node that feeds the function, activation function.
Yeah, like your new input has two things. It's a linear function on the current input plus another linear function on whatever just came out of the output before. Apply the activation function. Yeah.
Yeah, and for training, I think one of the tricks you can use is you unroll the loop and you basically say there is a hidden unit and it was giving an output and you were drawing this loop. Now instead of drawing this loop, break that and say, okay, this is going to some node, and then some node is giving it an additional input, right? And so then your contributions, you can separate them as, okay, this is coming from one place, this is coming from another place, and then apply a slight variation of backpropagation to that. So you are slightly approximating things at that point, like by assuming that, oh, I don't know where that input is coming from, whereas it is coming from my own previous output. But it still works well. One of the reasons it works okay is because these are all iterative procedures. And in each iteration, you're slightly tweaking the parameters. So an approximation works well for this training.
Yes.
You mentioned an approach was avoiding overfitting with neural networks by randomly dropping particular features. It sounds analogous to what like a random forest model would be doing with regression trees. It's just somebody's built a general purpose automated process on top of it. Is that something that either exists or could exist for deep neural networks, or is that something where they're like computationally you could never have something as general purpose because it was too much data, too many iterations that you need to go through.
So let me get a shot, and then you talk. I think basically how I think of training random forest is you train it, then you look at what the sort of errors were, look at kind of maximize, weight them more, then you train it again, then you do it and you train it several times. In a neural network, since training is very expensive, you kind of want to do things inside the training. So the mental picture that I have for dropout is if you're, I don't know, playing many sports with one hand, and then all of a sudden you're got a bicep here and nothing here, then one day you just, with some probability, you tie this hand and have to work with this one. So in dropout, it's like in the middle of the process of the dropout, you say, okay, in this part of this epoch, I'm gonna remove this node and see how the others do. And so it's more of a process that happens inside the training, whereas for gradient boosting, it happens outside of the training. Now, I don't know if you could do something similar than what you do with boosting by saying you train a network and then take the errors and weight them more and train it again. It could be possible. I don't know if anything. It probably requires a lot of computing power, but maybe I'll let Arpan elaborate.
That's a good point because, the way you do dropout is just randomly. So you're not really dropping them out based on any of their performance or weights. And one of the reasons you want to do it randomly is because you don't want to build in any of those biases, right? Like, maybe there is a node that has low weight. So it seems like it's not, adding much to the model, but maybe in certain specific cases, it actually affects how the result changes. So, so as far as dropout is concerned, I don't think we have that, but there could be other methods where you analyze the distribution of weights and look at the weights that are not, changing a whole lot over the training iterations and maybe drop them completely from the model.
Yeah.
That's possible.
Just a follow-up. Is the momentum, like when the rotor minima at the momentum and then shifted to the rotor minima for the global learning?
The momentum you said?
Yeah. The momentum.
Oh, like when you, so what I think of momentum is like if
You're not learning much.
yeah, like if you're training, right, and you're trying to get to the bottom of the mountain. Let's say your mountain looks like this. It has like a local minimum, and then the mountain. And you don't want to get stuck here, because once you get here, it doesn't point. You can't really point at the bottom. So what you do with momentum is instead of taking that step, you take the step and kind of average some of the ones before. So you have a bit of impulse, and then get over the hump.
Is it analogous to momentum with this value, like we are like dropping out?
I think of dropping out differently because dropping out is basically saying, in general, like dropping out and gradient boosting is like saying, oh, okay, if I have a weight that's too powerful, I don't want to just think of that one because that could be overfitting. So I want to like kind of shut it off for a minute and look and let the other was train. But when I think of momentum, I think of like not getting stuck in a local minimum and just keep going. So
Momentum is based on a pattern, definitely. But
yeah.
this dropout is just random.
Dropout is more random. Yeah.
Yeah, I think they're like, in terms of deep neural networks, I think those terms are used in different contexts. So, like momentum is used while looking at the actual training, like as an overall training metric, right? Whereas dropout, or I guess what we were talking about was, trying to analyze which features are contributing how much. Now, one way of thinking about it, yes, like it might be the same metric that you're using to compute the momentum versus to compute which features are contributing how much. But I would actually think of that as basically if you look at how the coefficients are changing over time for a particular feature, and maybe you can call it momentum, maybe not. But that's something that you can use to analyze features and see which are more important.